Hi, Hi everyone. Welcome to the IChemE Student Summit 2020. I trust you and your families are safe and well in these unusual times of COVID-19. I guess it's interesting that it is these unusual times that have brought us together. The fact that we can't meet face to face has allowed us to meet online and have the Student Summit. This is not just a gathering of students from one university or even those in one cities, I guess, nor even those in one state. It's a fact of a get-together from those of a similar time zones. I know we have students from Australia, New Zealand, Malaysia, Singapore, all registered. Let me just step back for a minute and introduce myself. My name's Peter Slane. I'm the IChemE Director for Regions. While home for me is in Melbourne, I am in fact an Auckland chemical engineering graduate. I've worked in oil refining, petrochemicals, food and dairy industries, as well as focusing on sustainability and climate change. You are students at a very exciting time for chemical engineering. You'll be graduating at a time when there are many challenges facing the world and with an uncertain future. The uncertainty puzzle is complex, but chemical engineering remains central to the delivery of solutions of many of these global challenges. The world needs answers in areas of sustainable water, energy, food and well-being. The breadth of chemical engineering puts you in a unique position to contribute to solving these global challenges. We hope your institution, IChemE, helps you on that journey and supports you to build your career. Over the next few days, you'll have a great range of speakers and a great range of topics. First, I'd like to acknowledge the traditional custodians of the land on which I work and live and recognise their continuing connection to land, water and community. I pay respects to the elders past, present and emerging. It is also with much pleasure that I introduce your first speaker, Trish Kerin. Trish also works for IChemE, and when we can all go back to our universities or our places of work, she sits near me in the office in Melbourne. While Trish did not do her undergraduate degree in chemical engineering, so forgive her for that, she is a mechanical engineer who has worked a lot of her career in the process industries of refining, oil and gas and chemicals. She's had a variety of roles from project engineering through operations, management and safety. She has assisted on government committees on safety as well. One Trish that's currently on is NOPSEMA, the offshore oil and gas regulator. She is now a chartered chemical engineer and fellow, and I know from experience that she will give you a great talk on process safety or whatever else she covers. So welcome, Trish. Thanks.
Thanks, Peter. And thank you, everybody, for the chance to speak to you today. It's very difficult times at the moment, and it's great that at least we can meet in this virtual environment and connect and talk about what's important about chemical engineering and the future of where we're going to go. What I am going to cover off today really is about process safety in the engineering profession, because that's the field I work in, that's the work that I choose to do. Firstly, just very briefly, want to mention a little bit about my background. So as Peter said, I'm a mechanical engineer, but I am now a chartered chemical engineer with IChemE, also a fellow of Engineers Australia, and with IChemE, a professional process safety engineer. I've spent my career working within the process industries, and as Peter did mention, I do currently sit on the board of NOPSEMA as well as lead the Safety Centre. All the opinions that I will give you today are that of myself, not the Australian government, nor NOPSEMA, and I do just have to make that declaration anytime that role's mentioned publicly. One of the things that I used to do a lot is cave diving, and this is actually a photo of me cave diving, and I often have people say, that's just ridiculous. What is a safety person doing something as dangerous as cave diving for? Why would you even think that was a good idea? But to me, cave diving is actually the ultimate in risk management. We know that there's really only one outcome if it goes wrong in a cave, and that is potential recovery. You're not going to be found and rescued. So it's very clearly a high stakes game. It is a high potential consequence situation that you need to apply all your risk management strategies to. You have to plan everything. You've got to do your risk assessments. You've got to be prepared for an emergency if something does go wrong. So for me, cave diving was really all about the ultimate in risk management. And that's why one of the reasons why I think I was attracted to it so much. I've now since retired, which is an example of how our risk tolerance can change. Over time, my risk tolerance changed and I decided cave diving was not for me anymore. But it sort of sets an important background to my career, I think, and some of the things that I've achieved in that. Just like to quickly acknowledge the members of the Safety Centre. Without these companies being part of the Safety Centre, we would not be able to do the work that we do, so it's important to acknowledge them. And also it's important to acknowledge the universities we work with all over the world, and many of you will be attending this summit from several of some of these universities listed on this slide, because we do cover a wide range of universities around the world. Okay, so let's talk about process safety. So what is process safety? Well, process safety is really about trying to prevent high consequence, low likelihood loss of control events. Now, they might be actual or potential consequence. Sometimes it could be what we call a near miss. It didn't quite go wrong, but if it had have just gone that little bit more wrong, it would have been really, really serious. And so the way we deal with process safety is we focus on things like leadership. Leadership is actually the fundamental underpinning aspect of getting good process safety outcomes. And it's leadership across things like knowledge and competence, engineering and design, systems and procedures, assurance, human factors and culture. All these elements are critical in getting good process safety outcomes in what we do. And so that's why we tend to focus on them in process safety, in the Safety Centre, because each one of these areas is an area that we have to really look after in what we do. I want to talk to you a little bit about my lessons in process safety. So I'm actually going to take you through 3 particular incidents in process safety in a little bit of detail. The first 2 are actually incidents that I was involved in. The third one I was not directly involved, but they shaped how I approach engineering and process safety. The first one is an airport fuel hydrant, and this incident happened very, very early in my career. I think I was only 1 or 2 years out of university when this incident happened, and I was designing and installing a hydrant fueling system at an airport. And we had this vent valve assembly, as you can see shown on the screen here. So there's a ball valve and a dry brake coupling that you would connect a hose on, open the ball valve, and you can actually vent air out of the system as you're flooding it with product again. Now, what I failed to realise at the time, and what the mechanical fitter who assembled this assembly also failed to realise at the time, is that that ball valve had a long and a short side, which meant that from one flange to the centre of the ball was longer on one side than on the other. Now, that shouldn't be a problem, except the ball valve was installed upside down. Normally, that wouldn't be a problem because it's a ball valve. But the issue is that when you connect a hose onto the dry brake coupling, and the dry brake coupling is a plate with a spring-loaded spindle on it, that spindle can protrude through the bore of the ball valve. And so when it came time to close the valve, because we'd vented out all the air and we now had product coming out of this line, we couldn't close the ball valve. And we tried to close the ball valve so hard that we bent the spindle, but we didn't know at that time that we'd bent the spindle. So being the young engineer, I thought I knew everything, thought I knew how to solve the problem. I said, we'll disconnect the dry brake coupling. That will cause the spring-loaded plate to close, except we'd bent the spindle. And so the plate didn't close, it wouldn't move. And so we then had a significant leak on our hands that we had to isolate and deal with and address. Now, there was only a couple of minor injuries in this. And in fact, I was the one that suffered the most injury because I ended up with jet fuel on my feet for quite some time before I was able to actually remove it. And I suffered some chemical burns. So there was no serious injury in here. And I didn't realise at the time, but this was a process safety incident. We had failed to contain product when we should have contained it because we didn't assemble it right. And I didn't know enough to do the checking to make sure that it was assembled right. And that's how we ended up in that situation. So that's the first example of a process safety incident in my career. The second example was a pipeline. And I was in charge of pumping product through this pipeline. This pipeline had a temperature rating of 55 degrees. And it was a 300-pound pipeline. So very heavy rated, reasonable high temperature pipeline. I allowed product to go through it that was at slightly higher than 55 degrees. And every single flange, the entire length of that pipeline, leaked because of thermal expansion. So you can see here in this photo, the pipeline comes out of the ground and it's obviously fairly well anchored at that point. And then it's got this big concrete block on it. On the other side of the flange, it's fairly well anchored there too. Every one of those flanges sprung a slight leak for the entire length of that pipeline because I didn't realise what I was doing. I thought it would be okay. I took a guess, and it wasn't a very good guess. I was running at very low pressure, nowhere near the 300-pound rating, but the thermal expansion got me on that one. No injuries, no incidents, no environmental impact in an ongoing sense either, because we're able to very easily pick up any remnants of what spilt. The reason the product was so hot was because it was a very thick product, so literally a shovel was able to be used to resolve the environmental impact in that instance. But another example that at the time I didn't realise, and it was a result of me really not knowing what I was doing. And so what I needed to do is sit back and reflect on these incidents and really understand what caused them. And I would say they came down to, in both instances for me, knowledge and competence. I didn't have the knowledge nor the competence to do what I was doing at that particular point in time. I should have questioned, I should have asked different questions. I should have further understood some of the background of what I was doing, but I didn't. And so on reflection, they were two process safety incidents that I was involved in fact, the cause of, you could say, early in my career. And they really started to shape my thinking about when things went wrong and how to deal with emergencies and how to prevent emergencies. And then another incident happened in Melbourne, in Victoria, in the town of Longford, where we saw an explosion occur at a gas plant. And 2 workers were killed in that explosion. And at the time I was working at a refinery, and we got a phone call to say there'd been an explosion at this plant. And that really hit home to me that day, because we turned the radio on and all of a sudden we heard that there were 2 workers missing. And I remember the looks on everybody's faces in the refinery planner's office when we just looked at each other and we knew they weren't missing. Because if they were missing at that point in time, they had unfortunately passed. And so that really hit home for me. Longford was a turning point in my career, and it actually set me off on a path of working in safety and process safety. So it's really been a key aspect and what's driven the work I do. I'm going to talk to you about some other incidents now as well. So unfortunately, there's no shortage of incidents around the world. You know, if we think back, and this is before many of you were born, Mexico City, 1984, there was a LPG explosion that caused a series of BLEVs, or boiling liquid expanding vapor explosions, to occur in many of the storage spheres. There was between 500 and 600 fatalities in that incident, and somewhere between 5,000 and 7,000 severe burns. One of the most significant incidents to have occurred. Sadly, it's not the most significant incident to have ever occurred. That rests with Bhopal in the very same year. Bhopal it's a town in India, and there was a chemical plant there. At that plant, they released some toxic vapors over the town whilst people were sleeping. It happened in the early hours of the morning. And that incident is estimated to have killed between 3,000 and 5,000 people that night, with a further 200,000 people injured. So Bhopal today is still the largest incident that we have seen, and hopefully it remains the largest incident we will ever see, because it is still a significant issue for us. But we learnt a lot from Bhopal. Herald of Free Enterprise is one that sometimes we talk about in process safety, and that surprises people because it's a ship. Why would we be talking about a ship? But actually, it really sums up a lot of the issues that we want to talk about in process safety. If we think about it being high consequence, and we think about it being a low likelihood event, this certainly ticks those boxes. It was a loss of control. They set sail with the bow doors open. It was a ferry where you could drive your vehicle onto. They set sail with the bow doors open, and it subsequently capsized, as you can see here. There are 193 fatalities on that ferry. That was running from Zeebrugge in Europe mainland. Piper Alpha. This is the incident that actually really focused us on how to do permit to work activities in our facilities. How do we control activities and work? And in fact, the anniversary of Piper Alpha was only last week. 167 men died that night when Piper Alpha had an explosion and fire and sank. One of the most significant oil rig incidents that we've had. certainly from a fire and explosion perspective, but it really changed the way we look at process safety on oil rigs, as well as looked at how we dealt with permit to work and safe work activities in the work we do. Texas City Refinery. Now, some of you may remember this. This was only 15 years ago. There was an explosion in the refinery when they were restarting up one of their processing units after a shutdown, and 15 people were killed in that explosion. There's a lot to learn, in particular around organisational culture, as well as locating of offices and temporary office accommodation on facilities during shutdowns as well. So still, a lot of incidents have given us learnings on what we can do differently. And also almost 15 years ago, coming up in December, is Buncefield. Now, Buncefield is an incident that happened in the UK. It was a fuel storage facility that had an explosion. A tank was overfilled, that released a vapour cloud, and that ignited and exploded. Fortunately, no one was killed in that explosion. There was substantial environmental impact that did occur, though, because there was a lot of firewater runoff that was contaminated with product and firefighting byproducts as well as foam. And so that has created some ongoing environmental impacts in the surrounding areas. So they were all at least 15 years ago. Where was the industry 10 years ago? Well, sadly, 10 years ago, we were still having explosions and incidents. And some of you may remember Deepwater Horizon. So this was an oil platform out in the Gulf of Mexico. And there was an explosion on this platform. It was an ignition source of the blowout preventer failing and a kick rising up to the platform deck. 11 people died in this incident. Now, this is an interesting incident from the perspective that that very day, senior executives from the company were on board to celebrate a great history of no lost time injuries. And later that evening, it had an explosion that killed 11 people. This is a really clear lesson to us that we can't focus on lost time injuries and standard OHS-related incidents to tell us anything about process safety at all. They're two completely different fields, and we need to make sure we look at and address process safety. Now, there's a lot of great work that's come out of looking at how we deal with process safety, particularly process safety culture, understanding different aspects of process safety culture as a result of Deepwater Horizon as well. So there's still always learnings coming out of these incidents. For something else completely different, that same year, there was a significant explosion that occurred in San Bruno, California, and it was a gas pipeline. So a standard gas main running through a suburban area. It was a 30-inch gas pipeline, and it ruptured, and then that gas that was released found an ignition source and exploded. It produced an enormous crater, and 8 people were killed in that explosion. The interesting thing was it happened just near San Francisco Airport, and for a period of time they actually thought a plane had crashed because they had no idea what was going on. The gas company didn't even actually know they had a leak at that point. There was a lot of issues around the maintenance and the integrity. So we can build something, we design it as engineers, we supervise its construction, it gets built, but how do we maintain it? How do we ensure it keeps its integrity so that we don't have a pipeline rupture at some point in the future, release tons and tons of flammable gas that can find an ignition source, destroy several houses, and kill 8 innocent members of the public because it exploded within their neighbourhood as well. So that was 10 years ago. What about 5 years ago? Well, 5 years ago, we're still seeing explosions. So this is a refinery in California again, Torrance, where they had an explosion occur. Now, fortunately, no one was killed in this incident. There was a significant near miss. There was catalyst that was deposited over the surrounding neighbourhood, but no one was actually killed in it. It was very lucky that no one was killed in it. So incidents can still continue to happen. So what about today? Where are we today? Well, we're in a very interesting situation today because we're all in, some form of isolation or some aspect of lockdown. So how are we maintaining safety in our facilities right now? Back in May, there was an incident at a chemical factory in India. And I have to admit, the moment I saw this first news report, I had a flashback of thinking about Bhopal. A toxic gas was released from a plant in India, and it engulfed the local suburb, the local township where people were living. I think so far the death toll from this has been 13 people. But there were actually people being affected lying in the streets. And that was, I think, what really struck home to me and hit about Bhopal and the comparison in there. So we are still seeing incidents occur today. Crude trains. So trains used in Canada to transport crude oil. You may have heard of an incident called Lac Megantic. So that happened 7 years ago in the small town of Lac Megantic in Canada. And 42 people, I think, from memory, were killed in that particular derailment and explosion. But there have been 7 major derailments in Canada since then that have spilt crude oil as a result of it. So when we're thinking about the engineering solutions we do for things, how are we thinking about transporting the products that we're transporting? Road, rail, pipeline, ship. There are many different ways to transport products. What are we putting into our trains or our pipelines, and how are we maintaining the safety and integrity of what's in those pipelines, or in this instance, trains? And you can see here the crude oil spilt over the snow as those train carriages leaked. So what can we do about it? You're all studying engineering. What do you need to do right now as you're learning, but also as you graduate and get into the workforce? How can you stop these sorts of incidents happening? Because actually, these are the sorts of things that we need engineers to be doing. We are the people that have the knowledge and the ability to prevent these incidents occurring into the future. So you need to actively participate in risk assessments. And sometimes, you've got your design projects, you're doing your activities, and you might think, oh, this is not really a serious risk assessment. Every risk assessment you do has to be thought of as being serious. If I go back to my cave diving, every dive I did a risk assessment for. It's not necessarily documented in the same way you do for process safety, but everything you do, think about what could go wrong. What are the hazards? What could those hazards lead to? What are the consequences? And what can you do to prevent that consequence occurring? Either reducing its probability of occurring or reducing the actual consequence, the magnitude of it. So how do you mitigate it? How do you prevent it? You need to think about that and then make sure you put that information in. Seeking out information and learning from incidents that have occurred. So I've just run through some of these incidents. Many of you will have heard of some of them. There's probably not many of you that will have heard of all of them, which is why I picked some of the ones I picked today. There's something to learn out of each and every one of these. Look for information. See what's out there. There's a lot of resources, both on the Safety Centre website as well as the Safety and Loss Prevention Special Interest Group website. There's the Loss Prevention Bulletin that you have access to as well. There's an enormous amount of resources out there. Learn about what happened, what caused those incidents, and what do you think you might have done differently? And think about that when you do get into the workplace and start to look at how people do different activities and do different tasks in the workplace. And instead of thinking, well, that won't happen here, actually ask yourself, how could that happen here? What would need to change, or what would need to fail in our system when you're out there in the workplace? Whether it's just as a summer vacation job, or whether it's you've graduated and you've gone into the workplace. And ask yourself, how could that incident happen here? What do I need to do to prevent that incident happening here? And importantly, also remember that when it comes to safety, you need to look for evidence of safety, not the absence of incidents. So start to think about safety from the perspective of, how can I make sure that there is actually safe activities occurring, rather than assuming things are safe just because we haven't had an incident in something? Because if you think about it logically, the absence of one thing does not mean the presence of another. The absence of an injury doesn't mean we're safe. We might just be lucky. And I certainly don't want to be relying on luck to keep myself or other people safe. because sometimes luck turns. So you've got to make sure that we're relying on evidence and information. How do you know it's safe, rather than just assuming it must be because, well, nothing's happened yet? There's some of the pitfalls that people can fall into in safety, and how we go about that. And the last thing is, just remember as an engineer that everybody has a right to not get hurt. What can you do in your role to make sure you help uphold that right for everybody? Because no one should go home hurt at the end of the day. But what are you doing? How can you contribute to making your workplace or your university setting as safe as possible, so that everybody has the right to not get hurt in what they do and go home safely at the end of the day? So we're going to have questions at the end. I will now hand over to Peter, and he will take you through the next presentation. Thank you very much for listening, and I'll take your questions at the end.
Hello, everybody.
Peter Mullinger is the next speaker. He's from Adelaide University. He's been I'm going to emphasise, very, very active member of the South Australian chemical engineering community. There's been a number of times, Peter, that you've talked to me about furnace tips or taught me a lot about combustion. And Peter has also been very active teaching design at Adelaide University. He's a chartered chemical engineer and a fellow of the Institution of Chemical Engineers. Welcome, Peter. Thanks.
Thank you, Peter. So I'm going to basically talk about my career, and it will give you a perspective of how chemical engineering has changed over the years. So we're having difficult and interesting times, and it's not the first time in history, of course, and it won't be the last. But one of the important things to recognise is every crisis produces opportunities. You may not see them at the moment, but the reason I ended up as a chemical engineer rather than mechanical engineer, because like Trish, I trained as a mechanical engineer, was because of various crises along the way that had to make me flexible, adaptable, and strive to be a team member. These are the keys to success, I believe. And we've got to expect change. Some of us don't like change, but it's always happened. So how did I start to be a chemical engineer? Well, I started in 1960. In fact, 60 years ago this month, I got a job at Hanley Engineering, and they gave me really big toys to play with. And you can see this is a large oil burner on test for Singapore Power Station back in 1960. And I was immediately aware of the dangers. It is obvious when you look at that flame, it's potentially dangerous. And it's potentially dangerous if it goes out and doesn't relight, for example. You get a huge accumulation of fuel. There's bound to be an ignition source around somewhere. It will then ignite and there'll be a massive explosion. So one of the first things I did in the first months I was in this business was actually to rebuild, because I had a real interest in electronics and electrical stuff in those days, I still do actually. So one of the first things I did was actually to rebuild a safety interlock system for a burner. And it was a relay-based system, and it was designed such that any wire broke or any contact failed to mate correctly, the system shut down. So it's essentially a fail-safe system. And we still have yet to reproduce that in computers. So that I had a very early introduction to process safety, but my interest in safety actually arose, and this is not a safety talk, that's Trish's role, but my interest in safety arose as a result of my interest in railways, because railways were the first people to have high consequence, infrequent incidents or accidents. So railways suddenly in early 1840s, invented new ways of killing a lot of people at the same time. And that led to the world's first safety legislation and the Railway Inspectorate, which was probably the first safety organisation in the world, the Railway Inspectorate in the UK. And it was staffed with Royal Engineers, so professional engineers investigated the accidents. And they had a no-blame culture. The idea was to find the cause and prevent it happening again. So that was my very early days. What was chemical engineering like in the 60s? I was a mechanical engineer. Chemical engineering was very, very intense state of flux. Plants were small, but they were rapidly increasing in size. In fact, I was working mainly in the power industry through my connections with Hanway Engineering. And turbo alternators increased almost magnitude of 10 times in just 10 years. So we were designing 500 megawatt units before the 120 megawatt units had even been commissioned. So there was a lot going on, and there was a lot of, shall I say, ignorance. We had no computers. All calculations were slide rules and log tables. There was increases in the number of plastics being produced, massive increases in hazardous processes, and the first LNG transport. This ship, the Methane Pioneer, was converted from being a small cargo ship into the world's first LNG carrier in the late 1950s. So it was an intense time of innovation in the UK, where I was born and still living at that time. Unfortunately, those innovations gave us a lot of problems. So this rapid increase in plants resulted in, with a poor understanding, produced accidents. Now, these accidents occurred even before the ones Trish was talking about, but they're basically awfully similar. It's scary. So, Freysian in France, LPG, another big LPG explosion. Flixborough in the UK, caprolactam, a volatile hydrocarbon. I teach this to the students. This one in particular was very similar to Trish's talk about the airport valve, the hydrant system for refueling at an airport. This was caused by a sampling system that was improperly designed, valves open in the wrong direction, and massive explosions. I can remember these. I'm old enough to remember these. In response, ICI developed HAZOP. And they also emphasized the responsibility of line managers for ensuring safe operation. This was world-changing philosophy at the time. 1970s, what also happened? The oil embargo. OPEC had an oil embargo. The price of oil increased 400% over a few days. The weekly wage was about $30 at that time, US, and the oil price went up to $12 a barrel. Major recession, major transport disruption, stimulated oil and gas exploration and production. The North Sea, Piper Alpha was in the North Sea. It was one of the products of this recession or this embargo. We got the Bass Strait off Victoria, North Wales Shelf off Western Australia and the Cooper Basin. In the UK, we had the Health and Safety at Work Act in 1974, and it made the site occupier responsible for all safety on site. This was a major change. Prior to that, the subcontractors, the individual employers on the site were responsible for safety. That wasn't working. What happened is major companies used to basically contract out all the dangerous work to subcontractors who weren't qualified to deal with it. So the Health and Safety at Work Act made the boss of the site responsible for everything that went on that site. And there were heavy penalties, including prison. And it was effectively enshrining the ICI approach in law. And that was world beating. And the Health and Safety Executive in the UK is a great source of safety information. A lot of their reports are available free of charge on their website, including Bunsfield, and you can go there and download them as PDF files. Have a look. Okay, so what else happened in the 70s? Oil was replaced wherever possible. So natural gas had just been discovered in Europe and just been discovered in Australia in the 60s. So natural gas replaced oil in the chemical industry largely. Coal was cheaper than gas, so where sulfur and ash were tolerated, that would replace them. So it replaced them in cement and lime making. Oil was still used where coal and gas were impractical because there was no gas, or coal was unusable. So in the 1970s, in my part of my life, I took myself off to the University of Sheffield in the beginning of 1970. I got a job as a contract researcher to increase my skills in oil burner design. So I was doing this work on oil burner design, on atomization, and I graduated exactly at the time that the oil price went through the roof. So I had to find a new career. So I couldn't design burners for power stations anymore because no one was going to build one. Not oil fired anyway. So I shuffled myself gradually into the process industries. I got a job in the cement industry, and in the early 80s, in the early mid-70s, and there I learned about coal. I learned about a lot of things. I had a lot of fun. I had a job which had an amazing job description, which was, my boss came to me one day, the technical director of Rugby Cement, and said to me, Peter, he said, you know about combustion, you know about heat transfer. We've got 21 kilns. Our coal is our biggest bill. You must be able to find something to do. And he gave me a free rein to find out what made these kilns tick, how they operated. And I did that by developing a cooperation with the University of Surrey, where they were doing a lot of modeling of the computer industry, modeling of combustion processes, and we started work. And we improved things dramatically. So I was enjoying that work, but then I got headhunted to head up a company in the oil industry, a combustion company, Europe's largest combustion company in the oil industry. I was asked to join that business as technical director to lead them into a time of better technology. First thing I did was buy them an Apple computer. This was the first computer, and it wasn't that long ago, 1980s, early 80s, the first computer that you could do sensible engineering calculations on, and it was affordable for a small company. You could do iterative calculations, and it reduced the cost of calculations and improved the accuracy. So that was an early stage of new technology. Things have moved a long way from there, of course, but that was a massive change. And it reduced the mistakes, which was one of the problems that had been plaguing this business. And it made the business profitable when it was unprofitable when I first joined. So that was early 80s. In 1984, I was not happy with that business because there was things going on in there which should not have been going on in terms of ethics. It was very important. Ethics have always been very important to me in my life, but put it this way, when we were discussing in a board meeting bribing an executive of a major oil company the price of $20,000 which is a heck of a lot of money in those days, to win a big flare job, I decided it was time I left. I looked around the world and decided there was no other company I could work for. I didn't see that any of the businesses that I had applied for jobs for, I couldn't see them as long-term businesses. And in fact, that is quite true. None of the companies I ever worked for up until that time are still in business. And I set up my own business, which is not a particularly brave thing to do. See, people say to me, weren't you brave? But it was something I had to do because there were no other options. So I set up my own business. And that was 1982. So then, of course, we had all these series of explosions and accidents that Trish has been talking about. And I was running essentially what was a combustion engineering business in the process industries. And you looked at these incidents, and particularly the last two, the fire in Mexico City and the Piper Alpha explosion, and insurance companies looked at us and said, you expect us to insure you? Yeah, that was the sort of problems we had. But we managed, we survived. But this time in the early 80s, there was a lot of pressure on companies to reduce costs. Because the energy costs were high, everybody is forced to reducing costs. And I think some of these incidents, particularly Bhopal was under cost pressures. The product wasn't selling. They reduced manpower. They reduced their refrigeration bill. And this directly led to that particular accident. The LPG explosion in Mexico City, I can't comment on, apart from the fact that they did design the process incorrectly in the first place. LPG is heavier than air, and they designed a burn pit to burn off, which is a hole in the ground, which has got fuel burning in it as their main safety relief. A burn pit is not sensible when you've got a heavier than air product. So that was a poor error. And then Piper Alpha, of course, there was major pressure to produce in the North Sea. And if you look at the Piper videos and the histories of Piper Alpha, you will see that was contributing. Certainly the work permit system was the major cause, but the contributing causes, which made it far worse. So we have excessive pressure for reduced costs and or increased production. And that led indirectly or directly to new legislation in the UK called the Control of Major Hazards legislation. So all these types of plants were regarded as major hazards because they were the potential for large consequence, infrequent incidents. So that's the 80s, or part of it. So there we are. The high cost of energy, it did lead to major changes in fuels, great opportunity for combustion specialists, which I was, pure luck. But I had to change careers, move out of power generation into the process industries in order to maintain my work. So there's a mini boom. So what happened in the mini boom? The stock market values went up. Companies became overvalued. Sounds familiar? Stock market crashed 1988 and everything went bad. Interest rates went up. Overborrowed businesses failed. And we started to look at greenhouse gas emissions. It's the first time they were widely recognized as being detrimental. We'd actually known about greenhouse gas emissions since Arrhenius, the famous Swedish scientist who worked out the reaction equation. He did his PhD trying to work out the cause of ice ages. And he came to the conclusion that ice ages were being caused largely by changes of CO2 in the atmosphere. And he worked out by a very long-winded way using slide rules and log tables, he worked out the contribution of carbon dioxide to the Earth's temperature. And he did that in the early 1900s. And believe it or not, I was taught about this work when I was at school in the 1950s in chemistry. So it's not new. And you will see there I have a clipping from a newspaper in New Zealand. And New Zealand, in my opinion, New Zealand has some amazing contribution to the world. So they worked out, and it's in the daily newspaper or the weekly newspaper, the furnaces of the world are now burning 2,000 million tons of coal a year. When this is burned, uniting with oxygen adds 7,000 million tons of carbon dioxide to the atmosphere yearly. This tends to make the air a more effective blanket for the Earth and to raise its temperature. This effect may be considerable in a few centuries. Well, 1 century later, it's very considerable. So I think that is a significant contribution there. We understood it a long time ago, and yet we still have climate change deniers. One way of tackling them to say, well, look, CO2, if we didn't have CO2, we'd be the same temperature of the moon, minus 15 degrees. That's about right. So we've known about global warming, but it's only with the massive increase in scale of things that it's become a real issue. In fact, Iranians thought it was a good thing because Sweden would never have another ice age. Now that no one's quite so sure. Okay, here's a good example. This is Lake Louise in Canada, one of my favorite parts of the world. First time I saw this lake in the late 80s, this glacier was down here somewhere. This is where it was in 2010. If we don't address these issues, all those Columbia ice fields will be gone in 100 years. And it amazes me that the United States doesn't really take this seriously, because most of the United States drinking water actually comes from the Columbia ice fields in Canada. So they should be taking it very seriously. Okay, so where we were in the 2000s. China, the rise of China as a manufacturing power. It drove a minerals boom, especially in Australia. And we started to worry about peak oil. Now, the amazing thing is that we cannot predict the future. It's impossible to predict the future. People are always trying to predict it, but we can't. So in the early 2000s, we were worried about peak oil. There was an assumption that oil was going to run out very quickly. So there were many attempts to produce renewable oil substitutes, biodiesel and the like. I just joined the University of Adelaide, and I was working on clean coal projects, so-called. And where's all that now? All gone. We got coal seam gas, we got oil and crude from fracking. The barriers to success of clean coal programs is enormous, major complexity, huge quantities of CO2 to be captured and sequestered. There is enough storage, but you cannot get the CO2 stored at a high enough rate to sequester the CO2 for a large power station. The rocks just aren't porous enough. Consequence of all these things, renewable energy becomes a major industry. Where does that put me? Well, I'm now in academic teaching. My research program collapsed, and I thought that was fair enough. I sort of retired because there was no more research to do, and then I went back and started teaching again. So we know rise of renewable energy. Here's some challenges for you. These are real challenges that we have to solve. So on the left there, this is a 2,000 megawatt oil-fired power station, which was built in the 1960s, commissioned in the mid-1960s. I was involved in the commissioning of it. It generated 2,000 megawatts of power continuously with oil firing. It was based at Fawley on Southampton Water, and it took oil directly from the Fawley refinery next door. So we've gone from that, this continuous 2,000 megawatt generation, to this, to solar power, where we have intermittent generation, small installations, widely scattered, generating probably only for 6 hours a day, and varying periods during the day. So we've got this major challenge. It's intermittent, widely distributed and small scale. We need potential solutions for continuous supply. And that's a major role for chemical engineers, a huge role there. We just have to invest. Then we get the GFC. So 2008, we get the global financial crisis. Results in large debts. Business activity declines again. Oil price collapses. All the attempts to reduce oil, renewable oil are abandoned. Clean coal also abandoned. We've got a warming climate, driving more air conditioning, driving more to desalination. We need a lot of water. Sustainable water is one of our biggest issues. In fact, I sat on a conference back in 1984. We were looking at, it was an IChemE, looking at future water. We've got to search for new solutions to store renewable energy. The role of hydrogen is being promoted. I see water availability as a limiting factor. I don't know if anyone does the sums of how much water you need to replace even natural gas in our economy. It's a huge amount of water to make that hydrogen. Any of the hydrogen that leaks is going to, that water is lost to the planet. It goes up into the upper atmosphere. We're looking at things like molten salt to store thermal energy, better and larger batteries, all roles for chemical engineers. Okay, I think chemical engineering will remain critically important to address these challenges. In fact, I've never been sorry that I shifted from working in mechanical engineering to moving into the process industries. It's been more interesting, been more enjoyable, there's been more opportunities. I've been able to do a lot more things than I would have ever done in the if I'd stayed a mechanical engineer. So those are the sort of things which we need to focus on, and they're all jobs from roles for chemical engineers. One of the things I would say is we can't predict the future. The keys to success, though, are flexibility and ability to embrace change. A lot of us can't embrace change, and that makes it difficult. Change will always occur. Ongoing learning. When you graduate, the IChemE will put great emphasis on continuing professional development. I have been a very active member of that space, and it's one of the reasons I've been able to shift from being a mechanical engineer in the power industry to being an academic. Whoever thought I would be an academic? Not me, that's for sure. Get involved. Become members of teams. Team working is critical. A lot of students don't like team working, but you can't always choose your team members. You have to work with them, though. And you can work with people you don't like. And in my life, I've worked for two people I've liked, but can't work for. I'll talk about that one. No, I won't talk about those. So, new materials, innovation critical. Developing new materials is also critical. Most of our key advances through time have been dependent on the developing of new materials. So we had cast iron in the 1770s. Abraham Darby worked out how to make cast iron smelting it using coke. And that cheapened the iron dramatically, because prior to that they had to use charcoal. World's first iron bridge was built in Shropshire in the 1770s. Steel, the 1880s. Thermoset plastics, Bakelite in the 1920s. Polythene and nylon developed in the 1930s. Not widespread use until the 40s, but they were developed in the 1930s. Semiconductors, chips, 1940s. Battery materials, 1990s. Graphene, maybe. What new materials are we going to produce? But we have to produce new materials to do new things. We certainly need greatly improved battery materials. Personal view of these things. Be patient. Typically it takes 40 years for a new advance to become widespread. Now, we are in the habit of saying today, things are happening more rapidly than they were. It's not actually true. The first steam locomotive, high-pressure steam locomotive, ran in 1804. 40 years later, there were 22,000 route miles of railway in Britain. 22,000 route miles built in 40 years by hand, largely by hand, most of it double track. That's an enormous achievement, and it made a huge difference to people's lives because people could move for the first time. Ordinary people could move for the first time. Computers, it's always claimed that computers have actually developed very, very quickly. But no, they haven't. They were actually invented in 1943. The first computer was at Bletchley Park in 1943. They didn't come into general use until the Apple computers came out in the early 1980s, late 1970s. Another 40 years. Mobile phones were actually invented in 1947. Again, we didn't get them in general use till the 1980s. So there we are. Remember, many attempts, not everything's going to work. Many attempts end in failure. Large-scale fuel cells, I worked on heavily at one stage, didn't get far. That's when I was running my own business. We supplied burners for the reformers for fuel cell power plants. Renewable oil production didn't go anywhere. Attempts to develop low-emission coal utilisation didn't go anywhere. Reasons for failure, often it's very difficult to scale this equipment. You can't scale it, or it's difficult to scale, or it cannot be made cost-effective. If we can't make things cost-effective, then we're not actually going to be able to get it into general use. Okay, some concluding remarks. Take opportunities when they arise. Don't be afraid of a challenge. Be prepared to move out of your comfort zone. It can be great fun. Learn from your mistakes. We all make them. Trish talked about a few she's made. Admit them and move on. Learn from them. You must learn from them, though. If a job's not working out, fix the problem. Change jobs or start your own business. Don't be afraid to change jobs for less money. I've done that 3 times in my life. Stay flexible. The world's been in constant change for 2,000 years. Industries come and go, employers change. Your basic skills are transferable. Keep learning. One of the best bits of advice I got was from an old mining engineer at Rugby Cement called Paul Dennison, who said, "The day you stop learning is the day you start dying." I'm 75 now, and that really has hit me. I've kept that in mind almost every day. And I'll finally end with a few books that I found inspirational. These have influenced me greatly. These are books I generally read when I was younger. I've read a lot of them again in more recent years. Frank Whittle, the inventor of the jet engine, a story of absolute perseverance against insurmountable difficulties, almost insurmountable. Relied on new materials to be developed. Neville Shute's slide rule. He was a novelist. He moved to Australia, but he was actually an aircraft engineer, and he wrote a book about his experiences starting a business and running a business and handing it over to new owners. Great inspiration for me. I understood what to do as my business was taken over by new owners. Schumacher, small is beautiful. Economics of people mattered. He was really pushing the fact that if we go over mad, he was pushing sustainable production. He was the first person really promoting sustainable development. Trevor Klett's What Went Wrong, Case Histories of Plant Disasters, read them. They'll stop you doing a lot of things wrong. Hudson Fish, he was the founder of Qantas. It explains his early days at Qantas and how intense safety culture was embedded from day one. It's amazing reading. He knew things were going to go wrong. What do we do if things go wrong? How do we prevent killing people? It was a major 1920s we're talking about now. And then finally, Richard de Crespigny. He was the pilot of the Airbus A380, had an engine explosion over Singapore, destroyed the controls, which basically made the plane unflyable. But he managed to land that plane, or his crew lands that plane, because of that intense safety culture embedded by Hudson Fish. So those are some important things that I recommend. Read those books. They're fascinating. So I'll finish up now. That's the end of my session, I think. And I'll be ready to take questions when you move on.
Great, thanks, Peter. Thanks for that. I'm looking at time, 4 o'clock. We're on time. I'm not sure how long we've got for questions, but someone will prompt me. And I saw a large number of questions come up as well on the sheet, and they disappeared from time during otherwise. So I'm not sure if someone can put them up again or see them again. In the meantime, I guess I've got a couple of questions. One for both of you, I guess, is how do you pass on learnings from one generation to the next? Have you got any suggestions?
I wish I knew that answer. I remember somebody once saying to me, networking is very important. You basically meeting people, talking to people, learning from people. You can only pass things on one-to-one, really. I wrote a book or contributed. I was the lead author of a book on furnaces because I wanted to pass on my knowledge in that space. And every time I open that book, I can see areas where I've got knowledge that didn't get into the book. It is so hard. And I also remember reading once, or hearing, I can't remember which of those, businesses do not have memories. It's only people who have memories.
I think from my perspective, if we can make the stories engaging and we actually use storytelling as a way to share information between generations, but that means we do need to make the stories engaging and interesting for people so they want to hear them. Humans learn a lot through storytelling. If you think about it, as we grew up as children, we had nursery rhymes. They were actually teaching us life stories.
Yes.
It can be interesting sometimes to go back and look at some of those nursery rhymes because as adults, we forget those life lessons. One of my favourite sources that I often just go back to for various different things, and I've actually done a presentation on it, is Dr. Seuss. There's some amazing lessons on leadership and culture and doing the right thing in Dr. Seuss. And that is a great way to start a conversation because all of a sudden people say, why are you talking about Dr. Seuss? And you can start to have that conversation. It gets people interested. And I think that's a really good way to try and get that intergenerational learning happening. Don't expect someone to go away and read it. Actually have this storytelling conversation.
Yeah, but that's really difficult, isn't it? Because it's a one-to-one still, that conversation, or one to small groups.
Yeah.
That's the real reality.
I think that's a big question. We've probably gone on for a while, but a number of questions have come up. So let me just go through them briefly in chronological order. They've been vetted, I think, by the students as well. Do you think Peter, do you think changing trends in the power sectors in terms of cheaper, safer, or cleaner fuels and technologies enforces chemical engineers to adapt to the situation? What do you think would be the next step in the near future?
Oh, I wish I could answer that one. When I wrote the second edition of my book, they asked me to predict the future trends. Now, that was only 2014. I got every one of them wrong. Every one of them was wrong.
Excellent.
So, look, I don't think you can predict. I think all you can do is prepare and be flexible and look at the opportunities. But batteries clearly is an opportunity. Whether batteries will do it, I don't know. I can't see a battery being able to keep power on for several days, of cloudy days and still days, for example. Diversity. Trouble with diversity, lots of different means of power generation is expensive. I actually don't know. But what I do know is you must be flexible and be adventurous.
And I think what you also said was allow yourself to make a few mistakes. So
yes, you're bound to. When I was 16 at Hanwith Engineering, one of my a fitter, he was just a fitter, but he was very bright. And he said to me, his name was Dave Spicer, and he said to me, Peter, I cut some pipe off too short. He said, Peter, and it was all men in the industry in those days, he said, Peter, the man that never made a mistake never made anything. Cut some more.
Yeah, okay. One for you, Trish, from Gav. Does good process safety also correlate strongly with good corporate culture and behaviour? Have you had similar experiences in your career?
It certainly does. Where you've got good corporate culture and behaviour, it actually leads you to making the right decisions and ethical decisions. Because often when we're making decisions that relate to process safety, they do come down to ethics and making sure that we've got the culture to learn and the culture to be willing to take a risk, but a calculated risk, that we know what we're doing and we've assessed what the consequences could be and we've implemented controls to try and deal with them. So process safety is actually all about strong discipline in what we do. Good corporate culture is all about strong discipline as well. It's all about having those assurance processes, the checks and balances in place to make sure that things are being done. So they certainly do go hand in hand together. I've had the opportunity to work for some companies that showed really strong corporate ethics in what they did and how they did things. And they were the businesses where we were able to make great advances in process safety, because if you took the time to explain what you wanted to do, people would understand and they would make the right decision based on the information. So, yeah, they certainly are very well correlated together, as we see that in general, good process safety and good safety outcomes in business. And again, I'm talking about the positive safety lead indicators, not necessarily just the lag indicators, are actually the businesses that do better financially, because they do have the discipline. And it also is very expensive to hurt someone, but you can make money when you actually have good productivity, and you get good productivity from reliability, and you get good reliability from asset integrity programs, which come straight back to process safety.
Great, thanks, Trish. Mortaza's asked, how does the advancement of technology, smartness, increase the safety in chemical processes, and how willing the companies are to adopt these advanced technologies to increase safety? Not sure who would like that, Trish.
I'll start with that one. I'm seeing a lot of willingness to adopt new technology in industry to deal with safety, whether it is using drones to do inspection, whether it is your digital twin setup that's allowing you to do training and actually create simulators more cost effectively, or even just augmented reality. We're seeing a lot of augmented reality devices now available. So we're certainly seeing a lot of industry interested and engaged and starting to fund some of that research to bring new technologies into their businesses to try and improve safety. So there's a lot of it out there. It's a really exciting space. The challenge I have in it is sometimes we need to be careful not to just adopt new technology because it's cool and sexy and new technology. It actually still needs to have a purpose of why we're trying to do it, what are we trying to get out of it. So you've always got to ask yourself, what's the safety benefit in this technology? But if there's a clear safety benefit, we're seeing companies adopt it.
Thank you, Peter. I was looking at you to see whether you had a comment. Peter,
I have a quick comment on that. With introducing new technology, we have to be careful, because when we saw computers come into process safety, we saw a big increase in the number of accidents, because people did not understand that computers can't be made intrinsically safe or fail safe. So there were large numbers of incidents that occurred because people didn't understand the technology. So I agree, new technology is really critical. You shouldn't stand against it, but you really have to be careful that it's going to be fit for purpose. And that's that's a real reality. And the early PLCs were not fit for purpose in this space. I remember having an argument with a computer company on a site in this country. I won't mention the site, but they put all the safety interlocks into the DCS, and there was no safety interlock system. And I said, well, that's not acceptable. And they said, well, it's fine. It's got a watchdog timer. And I thought, no, it's not fine. And I asked the operator to do an emergency shutdown. He had to scroll through 3 screens and then turn off the primary air fan to shut the burner down. And it was taken out by the interlocks. Now, that was completely unacceptable. But that was actually done, and it was done in 1988 in Australia. So, these sorts of things happen. If you've got the right safety culture in a business, then you will question that, but no one questioned it. No one actually understood what was happening. So yeah, new technology is really important. I don't stand against it ever, but it's got to be well thought out. And I think Trish's examples are well thought out, but this one wasn't.
Thanks, Peter. Thanks, Trish. Jack's asked a question. Peter, what are your thoughts on using nuclear energy as an alternative? Is this more or less viable than renewable energies?
That's a really curly question. Now, I have no fear of nuclear energy. I've actually, in my combustion company, we've designed plants for British nuclear fuels to incinerate radioactive solvent. I understand the safety aspects of it. And in fact, the reason I don't support nuclear energy is not on the basis of safety, it's on the basis of cost. Now, this little incinerator, which was to incinerate 100 kilos of an hour of kerosene, very, very simple process. If it had been a commercial kerosene, to burn commercial kerosene, it would have cost 250,000 Australian dollars. Because it was radioactive material, the system had to go in a cell, everything had to be austenitic stainless steel. The plant cost 20 million Australian dollars. Okay? So it's not that it's unsafe. If you ask me the worst way of generating, most unsafe power generation, it's actually hydropower. That's killed more people than any of the other methods because dam bursts. So it's not safety, it's cost. So viable, maybe one day, if we can get small, modular, cheap reactors that are really reliable, maybe. I'm doubtful.
Thanks. Thanks, Jack, for that question. Thanks, Peter, for the answer. That's good. Ashvin has asked what tips on how someone new to the workplace effectively discusses potential sensitive issues regarding safety with someone who is more experienced.
You want to go first, Peter?
I will go first. Yes, it's very tricky.
Yep.
It's very tricky. Firstly, you mustn't threaten. You must tackle it in a non-threatening way. If you go in a confrontational way, you're lost from day one. One way might be to ask questions that lead you to the point where the person you're discussing it with, actually, is your boss, basically, actually discovers the problem for themselves. So that's a technique I've used. For example, and it's slightly different, but my boss, when I was at Hamworthy once, we had a problem with an oil pump that was failing. And this little oil pump was supposed to pump thousands of gallons of oil over tens of thousands of hours. And this guy, whose name was Charlie Hardy, is a lovely guy, came into me and said, Peter, this is the answer to our problems. We have the pump out of a V2 rocket, which is completely opposite specification. Like that V2 rocket engine pumps thousands of gallons an hour for a few seconds. And I said, Charlie, how long is that pump intended to last? What was the design life of that pump? And he suddenly realized how stupid this suggestion was. So yeah, that's the way. Don't challenge people. Try and talk to them and bring it out to themselves.
I absolutely agree. In fact, that is the precise method I try to use as well, which is genuinely ask them open-ended questions until they actually realise for themselves what the safety issue is associated with it. You won't actually need to tell them about it. You can get there by saying, so maybe I'm not understanding. Can you just talk me through how this process works or how this works or what we're going to be doing? And as they then start to work through it, you keep asking questions of them. They will get to the point themselves very, very quickly usually. And it's the best non-confrontational way, because Peter's right. If you're starting with a confrontation, it's going to go badly, guaranteed. If you start by asking questions and listen to their answers, then it'll probably go pretty well in the end.
Yeah, I think that's the same answer I would give as well. Ask open questions. So,
yep.
Mar-Alice has asked for Trish, a question for you. Would you say that the current situation with the pandemic has affected the approach of industry to process safety? If so, how? And she's thank you as well for the answer in advance.
It absolutely has. We're now doing things very, very differently. There is actually a webinar coming up in the next couple of weeks where I'll be talking about how risk assessments are being done in this current state of COVID. It's towards the end of this month. It's a free webinar that you'll be able to register from if you go to the IChemE Safety Centre website. On the IChemE side as well, though, there is a paper where we talk about all the different things that industry are doing and the impacts that have occurred today. Things like splitting up their critical roles into different teams and making sure those teams have no contact with each other. So if one team goes down with infection, the other team is still there as a backup. How they're doing risk assessments. It's interesting, we've seen some incidents occur that are a direct result of the COVID pandemic, where companies have shut down in an unsafe manner or started up in an unsafe manner, or instances where they're handling lots of ethanol because they're now all of a sudden making hand sanitizer and they never did that before. We've seen those incidents, but we're also anecdotally hearing feedback from companies saying, actually, our safety record's better at the moment because we're not being distracted by all these risk assessments and all these other activities, and we're not doing some of this maintenance right now that would potentially increase hazards whilst it's being done. But that's a temporary reprieve from incidents, because if you don't do your maintenance or you don't do your risk assessments, it's going to come and bite you at some point in the future. So check out the paper. If you go to the IChemE website, it's and the COVID hub, it's right on the top of the front page of the COVID hub.
Right, thanks, Trish. Avendish has asked one for you, Peter. What's a burn pit, and can you please elaborate?
A burn pit is a very primitive piece of equipment. It's basically a hole in the ground with an oil pipe for burning fuel oil, burning oil liquids, and a gas pipe for burning gases, and an ignition and a flare, a flame, a constant flame for igniting. That's what a burn pit is. They shouldn't be, in my opinion. I never heard of a burn pit until I became technical director of Air Oil Flare Gas, which is a company I mentioned in the petrochemical industry. And we used to basically sell the equipment for these things. And when I first got in there, because I'd come out of the power industry, which actually had a much better approach to safety than the petrochemical industry did in 1980, in my opinion, I was horrified. And then I went on to plants where there were no burner management systems on the burner, all manually operated burner with no safety shutdown systems. Again, horrified. So, yeah, a burn pit is something that you shouldn't have. If you put it into Google, you'll get it. You'll get one. You'll get pictures.
We had the ground flare go on the plant go off next to me, would wake the whole place up. Antonio asked the question, Trish, how would you say attitudes towards process safety have changed over the course of your career so far? And do you see it continuing to change in the future?
There have certainly been many changes, and a lot of it has been related to more realisation about process safety and about all the arms and legs of process safety. So I think early on in my career, there was keep the oil in the pipeline, and that was basically the extent of process safety very early in my career, and that was sort of it had evolved from the Flixborough days and a number of the other incidents that I mentioned as well. To then we started to realise at the moment it's evolved to the point where we realise that process safety has an enormous amount to do with people, not just engineering. So of the areas that I talked about in my presentation, engineering and design is clearly about the engineering aspect. But human factors, culture, assurance, systems and procedures, knowledge and competence, they're all about people. And so we've now evolved to the point of process safety in understanding it's about people, which means we need to work collaboratively with psychologists, ergonomists and sociologists to really get to the bottom of how we can design appropriately for people to be able to use it and make sure that it's easier for them to get it right than it is for them to get it wrong. So we're at that stage now, and I think it will continue to evolve and change. I think we'll see more focus going forward on engaging with people and how to get the best process safety results with people and equipment together, and that human-machine interface moving forward. But that's currently where sort of how I've seen that evolution from very strictly it's just about the engineering to realising it's about the people, and I think we'll continue to evolve further in that direction now.
Thanks, Trish. Just to check, Peter, you looking like you wanted to...
Oh, look, I couldn't agree more. I mean, I used, as I said, I ran my own business. I was very conscious that our people were most of the time out on plants. They spent time in the office designing things, and then they went out and commissioned them. I was very keen that all the engineers had a lot of site experience. I was very aware on site that they were at risk, and we put a lot of effort into process safety. And I would say for the just under 20 years that I ran that business, no one got hurt, apart from the odd cut and things like that. And we were working with dangerous kit. When you're working with combustion, you're always working with process safety risk. I do think that when you're working with process safety risk all the time, you become more aware of the risk. I think that's a lot of the time it's when people aren't aware of the risks of the issues. So it does. I agree totally with Trish. It comes down to people. Everything in the end comes down to people and how they're managed and how they're encouraged. That it comes out great in Hudson Fish's book. He just the culture there was just amazing.
Right, thanks, Peter. Ibrahim's asked, I'm not sure I'm going to say this right, what field, Peter, for you, Peter, what field of chemical engineering has more works or studies on?
Oh, no idea. I can't answer that question. I think it varies with time, but at the moment, a lot of it is in new materials. A lot of it, I think, is in particularly renewable energy and how we make that more reliable, more continuous. But I really don't know.
Okay, thanks, Peter. We've got a few more questions coming in. I think we've still got a few more minutes until someone corrects me. But Ashvin's asked a question on some tips on how undergraduates can expand their knowledge on process safety other than through university work.
One thing I'd quickly suggest is go and check out the IChemE Safety Centre YouTube channel. There is, there'd be close to 80 videos on there now, various webinars or also just little incident videos that we release on the anniversary of their incidents. It's just a little short snippet of information for you to then go and research a little bit further and understand a little bit more. So we've focused on putting a whole lot of information onto our YouTube channel. So it's really accessible and searchable for people. So there's a whole lot of stuff there that you can check out. as well as, read the lessons learned bulletins that various organisations put out. We put out one called Safety Law. The Centre for Chemical Process Safety put out one called the Process Safety Beacon. They're great, short, easy to read, just to give you a little bit of a learning. So I'd go and check out some of that material.
Yeah, mine would be the Disaster Cast podcast. There's podcasts on it as well.
Yeah,
Disaster
really
Cast, that start from Griffin University person.
Yep.
Yeah, there's a lot of information out there. I would also look at the HSE website, the Health and Safety Executive in the UK. They've got fabulous research laboratories. It took them a long time, a lot of research to work out really what went wrong at Buncefield, because the explosion pressures there were much higher than anyone had experienced before. And the fact that no one was killed in that accident is mere luck. It happened 6 o'clock Sunday morning. Everybody was at home in bed with their curtains drawn. The drawn curtains saved them from the broken glass. If the people had been at work the next morning on that industrial estate nearby, the death toll would have been in the hundreds. So they were just lucky. As it was, the damage bill was billions.
And there's the US Chemical Safety Board, if that's still published as well.
Yeah, great reports and videos there. And several podcasts. Chemical Processing, I do a podcast with them every few weeks as well. There's all sorts of great information out there.
And thank you for that. Ibrahim's asked another question. Peter, what field? Oh, hang on, done that one. I think that is all the questions I can see.
There's one more question here. I'll just jump in quickly.
Please do.
From Joshua. For Peter, starting your own business would be a risky career move for most. From your experience in the process industry, what knowledge does one need to know to make that move and ensure that Endeavour survives in the long run?
Well, my recommendation would be make sure you've got quite a lot of experience ahead of the game. I was 40 years old when I started my own business. I actually made the decision on my 40th birthday. It is high risk. We nearly went bankrupt at least 4 times, because when you face recessions like the '88 recession, we lost more than half our work, and I had quite a large number of engineers employed. I didn't want to lose them because of I couldn't replace them. Yeah, it's not easy. You need experience. You need mentors. Mentors are really important in my life. I think I've been very lucky in the mentors that I've found along the way, or have found me. I don't know how it happens exactly, but be an active member of IChemE, for example. I was an active member of the Institute of Energy, as it was in those days in the UK, and I started my business as a result of a chance conversation with someone from British Gas. Opportunities arrive, seize them, but be prepared to suffer. It's not easy. It's hard work, and you will suffer. You'll have a lot of problems. So I don't want to put you off, but I'm being realistic.
Thanks. Thanks, Peter. Thanks, Trish. So I'm going to say thanks to the speakers now for great talks, and I'm also going to thank the students or people listening for raising questions as well. And then I'm going to say thank you, everyone, and I'm going to pass over to the people behind organising this. I think they'll just take over the microphone from me. Thank you.
I just wanted to start by thanking Trish and Peter, our speakers today, for starting the week off with the yesterday aspect of our theme. So they've both introduced some really essential and relevant topics, engineering topics, such as process safety, greenhouse gas emissions, and new materials and technology, which chemical engineers are definitely lucky enough to be on the front line when it comes to those things. Something else that was a bit of a theme through both Trish and Peter's speeches was the topics of being flexible. And Trish, it sort of came through, that there's no room for complacency in chemical engineering when it comes to especially process safety. And as Peter drilled home, it's really important to embrace change and be flexible, which is something I think we will definitely be drilling home throughout the whole week. So the summit this week is themed chemical engineering yesterday, today, and tomorrow. And the organising committee chose that theme because we think it's really important for young engineers such as ourselves who are about to walk into industry to really understand where we've been as an industry and how that's informed where we are now and where we're going in the future. So I think Thomas has sort of already briefly done it, but I'm just going to quickly introduce some of our organising committee. So we have ChemS from Adelaide, which is represented by their president, Azzy, and their vice president, Jack. CHES UQ is represented by me. I am the president of CHESA here in Queensland. And we have RMIT Association of Chemical Engineering Students, which is represented by the VP, Danny, and the secretary, Nimish. We've got representation from Sydney University Chemical Engineering Society, and the president, Emma, is on our organisation committee. And from QUT, the Chemical Process Engineering Club, we've got Fiona Collins, their president. And down from Monash, Society of Monash University Chemical Engineers, we have Garv, and the Melbourne University Chemical Engineering Student Society, represented by the president, Lachlan. The Association of Chemical Engineering Students in Curtin, so all the way over west, we have the president, Olivia, represented, and the Chemical Engineering Undergraduate Society in UNSW, who we have Thomas, who was just speaking, the president, and the VP, Annie. So we've all come together in sort of an unprecedented gathering, you know, all of us from all across Australia to bring this event to fruition. And so I'm just going to quickly take you through what that's going to look like for the rest of the week. So as I said, we've decided on the theme to be yesterday, today, and tomorrow. And today we've touched on a little bit about that yesterday through the experiences of Trish and Peter. And tomorrow, Wednesday and Thursday, we'll be touching on the today aspect of the theme. So we'll be going through various disciplines in the chemical engineering world. So we've got energy and resources, sustainability and environment. And then Thursday, we've got a bit of biotechnology and pharmacology. But please take note that there is a trivia night on Wednesday, which of course everyone who's registered is invited to, and there will be prizes up for grabs. And then on the Friday night, we have a bit of a networking evening as well, because we think it is quite important in events like this to make connections, as Trish said and Peter said as well. It's an important way to keep learning, to make those connections in industry and also just with students from all over Australia. And just some housekeeping for the week in general. In each session that you do register for and get links for, your camera and mic will be automatically off. And I don't think you can turn them on, but if you find you have that capability, please keep them off during the presentations. And as you already have used, please ask your questions in the Q&A function that we've used today, and our MCs on the organising committee will ask those to our speakers throughout the week. And of course, prepare to ask questions and share knowledge throughout the week, because that's what it's all about. So that sort of wraps it up, I think. So from the 9 student societies that have organised this for students, we really hope you enjoy the week and take something from it. So thank you very much to everyone who's stuck around through those technical difficulties.